Hello children, now let us understand circular motion in vertical plane. Suppose a particle of mass m is connected with a light and inextensible string of length r. The string is fixed at point O. Particle is given a horizontal velocity u so that it starts moving on a circular path in vertical plane. At some point of time it is at point P so that line OP makes an angle theta with vertical. Point P is at a height h as compared to point A. Our reference line, which is horizontal, passes through point A. First, we will calculate h. H is OA minus OQ. OA is r, length of the string or radius of the circular path. OQ can be calculated from this right angle triangle, and that is r cos theta. So h is equal to r minus r cos theta. This is equation number 1. We can apply conservation of mechanical energy at point A and at point P. At point A, kinetic energy plus potential energy is equal to kinetic energy plus potential energy at point P. Kinetic energy at A is half mu square and potential energy at A is equal to 0 because point A is passing through the reference line. Kinetic energy at point P is half mv square. Suppose velocity of the particle at P is v. Potential energy of the particle at point P is mg into h. H we have calculated as r into 1 minus cos theta. From this, we get v square is equal to u square minus 2gh. Suppose this is equation number 2. At point P, forces acting on the particle are its weight that works vertically downwards, tension in the string that works towards the center. Component of weight that is along the line OP is mg cos theta. Since particle is moving on a circular path, so net force should work towards center, and that is T minus mg cos theta. That will provide the necessary centripetal force. So T minus mg cos theta is equal to mv square by r. Suppose this is equation number 3. From this equation, T is equal to mv square by r plus mg cos theta. Suppose theta is equal to 0 degrees, that is particle is at A. So tension in the string will be maximum and it is given by T max is equal to mv square by r plus mg. Put theta is equal to 0 here. When particle is at Q, that is theta is equal to 180 degrees, tension in the string will be minimum and that is given by T minimum is equal to mv square by r minus mg. Put theta is equal to 180 or pi here. Now let us understand 3 conditions. Condition of looping, condition of leaving the circle and condition of oscillation. First, condition of looping. In this condition, particle must be able to complete the loop. That means even at highest point, string should not slack. So tension in the string at highest point should be greater than or equal to 0. Put T is equal to 0 and theta is equal to pi in equation number 3. This gives mg is equal to mv square upon r, or v is greater than or equal to under root gr. Put this value of v in equation number 2. That gives u is greater than or equal to under root 5 gr. That means in order for particle to complete the loop, it should be given a velocity greater than or equal to under root 5 gr. Now from equation number 4, maximum tension in the string that will happen at point A is equal to 6 mg. From equation number 5, minimum tension in the string that will happen at topmost point is equal to 0. Second condition is condition of leaving the circle. If initial velocity given to the particle is less than under root 5 gr, particle will not be able to complete the circle. A string will slack even before the particle reaches at the topmost point. That means tension in the string will be 0. So put T is equal to 0 in equation number 3. This gives cos theta is equal to 2gh minus u square upon gr. Put this value of cos theta in equation number 1. This gives h is equal to u square plus gr upon 3g. Let us say this is height h1. So tension in the string is 0 at height h1. Now put v is equal to 0 in equation number 2. This gives h is equal to u square upon 2g. Let us say this is height h2. Particle will leave the circle if tension in the string is 0, but velocity of the particle at that point is not equal to 0. That means height h1 is less than height h2. So u square plus gr upon 3g is less than u square upon 2g. This gives u is greater than under root 2gr, but u is less than under root 5gr. That means u lies between under root 2gr to under root 5gr. Put u is greater than under root 2gr here. That gives h is greater than or equal to r. So h is greater than or equal to r means theta lies between 90 to 180 degrees. What it means is if initial velocity given to the particle lies between under root 2gr to under root 5gr, particle will leave the circle somewhere between points M and Q. Third condition is condition of oscillation. This condition is just opposite to previous condition. In previous condition, tension in the string was 0, but velocity of the particle at that point was not equal to 0. In this condition, velocity of the particle is 0, but tension in the string at that point is not equal to 0. We had got in previous condition h1 is equal to u square plus gr upon 3g and h2 is equal to u square upon 2g. In previous condition, h1 was less than h2. In this condition, h2 is less than h1. So u square upon 2g is less than u square plus gr upon 3g. This gives u is less than under root 2gr. If we put u less than under root 2gr, here we get h2 is less than or equal to r. That means height is less than or equal to radius of the circular path. So particle will oscillate somewhere in this zone. So if initial velocity given to the particle lies between 0 to under root 2gr, particle will oscillate. Let us summarize our learning. If initial velocity given to the particle lies between 0 to under root 2gr, particle will oscillate between theta 0 to 90 degrees. If initial velocity given to the particle lies between under root 2gr to under root 5gr, particle will leave the circle where theta lies between 90 to 180 degrees. When initial velocity given to the particle is greater than under root 5gr, particle will complete the loop. Let us see 3 questions based on work, power and energy and circular motion combined. First question, a heavy particle is suspended by a string of length L. The particle is given a horizontal velocity v0. The string becomes slack at some angle and the particle proceeds on a parabola. Find the value of v0 if the particle passes through the point of suspension. Suppose a particle is suspended by a string of length L. O is the point of suspension. Particle is given a horizontal velocity v0 so that it starts traveling on this circular path till point C. At C, the string slacks and particle leaves the circular path and starts traveling on this parabolic path. It is given that particle passes through point of suspension O. We have to calculate the value of v0. First, we will find out velocity of the particle at point C, that is vc. Suppose line OC makes an angle theta with the vertical. At point C, particle was on circular path. So component of weight that is along CO is mg cos theta. That will provide necessary centripetal force. So we can say that mg cos theta is equal to mvc square upon L, or vc square is equal to gl cos theta. Suppose this is equation number 1. We can apply conservation of mechanical energy at point A and C. So we can say that kinetic energy plus potential energy at A is equal to kinetic energy plus potential energy at C. Suppose we take a horizontal line passing through A as reference. So kinetic energy of the particle at point A is half mv0 square and potential energy of the particle is 0. Kinetic energy of the particle at point C is half mvc square and potential energy is m into g into this height, and this height is equal to L plus CD. In this right angle triangle, cos theta is equal to CD upon CO. So this will be L cos theta. So this height will be L plus L cos theta. So potential energy of the particle at C will be mg into L plus L cos theta. This gives V0 square is equal to Vc square plus 2gl into 1 plus cos theta. Suppose this is equation number 2. We can put the value of Vc square from equation 1 to get V0 square is equal to gl into 2 plus 3 cos theta. Suppose this is equation number 3. Now the particle will leave the circular path and start traveling on parabolic path. Suppose we take C as point of reference. Right side and upward we will take positive, left side and downward we will take negative. Horizontal displacement when the particle travels between C to O will be CE or OD, and we will take this as negative. So horizontal displacement OD from this right angle triangle will be minus L sine theta, and velocity component also will be negative, that is Vc cos theta, that is horizontal component of velocity at C. So it will be minus Vc cos theta into T. This is equation number 4. Vertical displacement of the particle between point C and O will be CD. From this right angle triangle, this will be L cos theta and will be taken negative. So minus L cos theta is equal to vertical component of the velocity will be Vc sin theta. That is Vc sin theta into T minus half gt square. Suppose this is equation number 5. We can put the value of T from here and Vc square from here to simplify it to get cos theta is equal to 1 by root 3. We can put the value of cos theta in equation number 3 to get V0 is equal to under root GL into 2 plus root 3. Second question, figure below shows a smooth track, a part of which is a circle of radius r. A block of mass m is pushed against a spring of spring constant k, fixed at the left end, and is then released. Find the initial compression of the spring so that the block presses the track with a force mg when it reaches the point P, where the radius of the track is horizontal. This is the figure given. Suppose a block of mass m is kept at A. It touches a spring whose other end is fixed to a wall. When the block is pushed towards the left, it compresses the spring by a distance x. When the block is released, the spring pushes the block towards right. It is given that when the block reaches at point P, it pushes the track with a horizontal force mg. We have to calculate the value of x. At point A dash, when the spring is compressed by a distance x, potential energy of the spring is 1 by 2 kx square. When the block is released, let's say its initial velocity is VA dash. So that potential energy of the spring is converted to kinetic energy of the block. So 1 by 2 kx square is equal to 1 by 2 m VA dash square. This gives VA dash square is equal to kx square upon m. Suppose this is equation number 1. At point P, block presses the track with a horizontal force mg. In return, track presses the block towards left, and that is normal reaction by the track. It is nothing but centripetal force. So we can equate horizontal force mg with centripetal force. Suppose at point P, velocity of the block is Vp. So Horizontal force mg is equal to centripetal force mvp square upon r. This gives vp square is equal to gr. Suppose this is equation number 2. We can apply conservation of mechanical energy at point A dash and P. Suppose this is reference line. So kinetic energy of the block at point A dash is equal to half mVA dash square and potential energy is 0. Kinetic energy of the block at point P is 1 by 2 mVp square and potential energy of the block is mg into this height, and that is radius of the circular path. This gives VA dash square is equal to Vp square plus 2gr. Suppose this is equation number 3. We can put the values of VA dash square and Vp square from equation number 1 and 2. This gives x is equal to under root 3 mg r upon k. Last question. Figure below shows a smooth track which consists of a straight inclined part of length L joining smoothly with the circular part. A particle of mass m is projected up the incline from its bottom. Part A. Find the minimum projection speed v0 for which the particle reaches the top of the track. Part B. Assuming that the projection speed is 2v0 and the block does not lose contact with the track before reaching its top, find the force acting on it when it reaches the top. Part C. Assuming that the projection speed is only slightly greater than v0, where will the block lose contact with the track? This is the figure given. Part A. Suppose the particle starts from point A with projection speed v0. It just reaches the top of the circle and stops there. We can apply conservation of mechanical energy at point A and at point P. At point A, kinetic energy of the particle is half mv0 square. Suppose this is reference line. So potential energy of the particle at point A is 0. Kinetic energy of the particle at point P is 0 because particle stops there. So kinetic energy at P is 0. And potential energy at point P is equal to mg into this height PE. PE is equal to PD plus DE and DE is equal to CB. From this right angle triangle, CB is equal to L sine theta. So PE is equal to PD plus L sine theta. We will calculate PD now. PD is equal to PO minus DO. PO is radius of the circle and DO we can figure out from this right angle triangle. First we will figure out angle COD. In this right angle triangle, angle ACB is equal to 90 minus theta. Angle ACO is 90 degree as AC being tangent to the circle. So angle BCO is equal to 90 minus theta. So this angle is theta. Since the angle BCO is theta, so angle COD is also theta. Now this angle is theta. So in this right angle triangle, DO is equal to R cos theta. So PD is equal to R minus R cos theta. So we will put this value here. So half mv0 square is equal to mg into R into 1 minus cos theta plus L sin theta. This gives v0 is equal to under root 2g into R into 1 minus cos theta plus L sin theta. Part B. Now the projection speed is 2v0. That means particle will not stop at P, it will keep moving. Since the particle at P is moving on a circular track, that means net force on it will work towards the center, and that is centripetal force. Suppose velocity of the particle at P is Vp. So net force we have to calculate, and that will be mvp square upon r. Apply conservation of mechanical energy at point A and at P. So kinetic energy plus potential energy at A is equal to kinetic energy plus potential energy at P. Kinetic energy of the particle at A is half m into 2v0 whole square. Potential energy is 0 at A. because this is reference line. Kinetic energy at point P of the particle will be half m Vp square and potential energy will be mg into this height Pe. We have already calculated V0 square and P in part A. So this gives 4mv0 square plus mvp square plus 2mg into Pe. Suppose this is equation number 1. We have to calculate mvp square upon r, that is net force at point P. So divide both sides by r. That gives mvp square upon r is equal to 4mv0 square minus 2mg into Pe upon r. Put the values of V0 square and P from part A, and that is V0 square is equal to 2G into R into 1 minus cos theta plus L sin theta, and P is equal to R into 1 minus cos theta plus L sin theta. This gives net force at point P is equal to 6 mg into 1 minus cos theta plus L by R sin theta. Part C. Now the projection speed is slightly more than V0. That means particle will not stop at P, it will keep moving on the circular track, suppose till point Q. At point Q, particle loses the contact with surface. Suppose line OQ makes an angle alpha with the vertical. We have to calculate the value of alpha. Suppose velocity of the particle at point P is Vp and at point Q is Vq. At point Q, net force will work towards the center, and that is component of weight towards the center, that is mg cos alpha minus n. N is the normal reaction applied by the surface that will work readily outwards. So net force towards the center will be mg cos alpha minus n, and that is equal to centripetal force, that is mvq square upon r. At point Q, particle loses the contact with the surface. That means normal reaction n will be equal to 0. Putting n is equal to 0 in equation 1 will give mg cos alpha is equal to mvq square upon r, or vq square is equal to gr cos alpha. Suppose this is equation number 2. Now we will apply conservation of mechanical energy at point P and Q. So kinetic energy plus potential energy at P is equal to kinetic energy plus potential energy at Q. Kinetic energy of the particle at point P is half m Vp square, and potential energy of the particle at P will be mg into this height. Suppose we are taking line Mn as reference. So this height will be r plus r, that is 2r. Kinetic energy of the particle at point Q is half m Vq square, and potential energy will be mg into this height, and this height is r plus r cos alpha, that is r into 1 plus cos alpha. Now value of Vq square we can put from equation number 2. Vp is negligibly small, so it can be approximated to 0. So we will get the value of cos alpha is equal to 2 by 3, or alpha is equal to cos inverse 2 by 3. In next video, we will solve previous year's JEE questions. If you have a question, you can ask me on my Discord server. If you have not subscribed my channel yet, please do so.